In this class, we are going to discuss about imperfections in solids. At absolute zero, solids tend to have a perfectly ordered arrangement at any temperature above 0 Kelvin. If the solids have some departure from the perfect ordered arrangement, this is called imperfections or disorders in solids. So we all know that at absolute zero, solids have a perfect arrangement. So the temperature above 0 Kelvin. 0 Kelvin means minus 273.15 degrees Celsius. The solids have some departure from the perfect ordered arrangement. So at a room temperature, the solids may have some departure from the perfect ordered arrangement. So this is called imperfections or disorder of solids. And this have an important influence on the properties of solids. Okay, these imperfections can be classified as four. Those are point defect, lattice defect, line defect. The last one is plane defect. Okay, in point defect, the imperfection is localized in a few particles. If the imperfection is extended over a wide region in a crystal, it is called a lattice defect. If the defect is along a line, it is called a line defect. If the defect is along a plane, it is called a plane defect. Okay. First, we are going to discuss about point defect. Point defect means what is point defect? If the defect is localized in a few particles called point defect. Okay. Point defect is arised due to mainly three reasons. Those are absence of a particle. The second one is particles are missing from their position and they are occupied in the interstitial position. The third one is the presence of impurity at the lattice. So these 3 points we will discuss later. The point defect can be classified as the following. The first one is stoichiometric defect. The second one is non-stoichiometric defect. And the third one is impurity defect. So, in stoichiometric defect, these defects are shown by crystals which obey the law of constant composition. So the crystals which obey law of composition will only show the stoichiometric defect. That is, if the defect do not disturb the stoichiometry of the compound. Okay, it is also called intrinsic or thermodynamic defect. This stoichiometric defect can be observed in ionic solids as well as non-ionic solids. So here I am discussing the case of a non-ionic solids. So non-ionic solids shows two types of defects. They are vacancy defect and interstitial defect. Vacancy defect means some of the lattice sites are vacant. Here this lattice site is vacant. So this is called a vacancy defect. And the second one is interstitial defect. It means when some particle occupy the interstitial position. Here it is occupies in the interstitial position. So these two are the examples of non-stoichiometric defects in non-ionic solids. In the case of ionic solids, there is also two types of defects are present. They are called Schottky defect and Frenkel defect. These are the two scientists who discovered this defect. Okay, Schottky defect means missing of equal number of cations and anions from their normal position and a pair of hole is formed. Then this defect is observed in ionic solids having high coordination number. Then ions of almost similar sized solids shows this. If the density of crystal is lowered due to the presence of vacancies in the crystal lattice, it slightly increases the electrical conductance. The examples are NaCl, KCl, CaCl, etc. Okay. Then this is the diagram. My drawing is not that much good. Okay. So in Frenkel defect, we already discussed that equal number of cations and anions are missed from the lattice side. So here a cation is missed and here an anion is missed. So a pair of holes is formed in this case. This pair of holes can increase the electrical conductivity. Okay. And so two vacant sites are formed. So this vacant site will decreases the density of the crystal. Okay, this is called the Schottky defect. So I think you understand this. The second one is Frenkel defect. Okay, it is arised when an ion, usually cation, leaves its normal site and occupies an interstitial site. Okay. Ionic compounds having low coordination number. So ionic compounds having low coordination number will show this defect. And crystals with anions are much larger in size than cations will show this defect. No ions are missed from the crystal, so it doesn't affect the density of the crystal. The examples are AgCl, ZnS, AgBr, Ag ions. AgI. Okay. So the silver halides are show this property, this defect. Okay. So this is the diagram. So this diagram we already discussed that. So what is Frenkel defect? Frenkel defect means a ion, normally a cation. So a cation is here, A plus. It is leaves from its normal position. Then it is occupies in an interstitial position. So this is called a Frenkel defect. So in this case, what happened? Because no ion is missed from the crystal lattice. That is why it does not affect the density of the crystal. Okay. Then AgCl shows both Frenkel and Schottky defect. Okay. The next one is non-stoichiometric bond defect. It means the compound which do not obey the law of constant composition are known as non-stoichiometric compounds. So the non-stoichiometric compounds means they does not obey the law of constant composition. Okay. This defect which disturb the stoichiometry of compound. So this defect can be disturbed the stoichiometry of compound. These defects are either due to the presence of excess of metal ion or the deficiency of metal ion. So non-stoichiometric bond defect can be classified into two. First one is due to the presence of excess of metal ion and the second one is due to the deficiency of metal ion. The first one is metal excess effect and this can be classified into two. The first one is due to anion vacancy and the second one is due to excess cation. The anion vacancy means a negative ion is missing from the lattice and leaves a hole, and this hole will be occupied by an excess electron to maintain the electrical neutrality, and this holes occupied by electron are called F-center. So note the term F-center, this is very important. It means the hole occupied by the electrons are called F-center. And this F-center are possible for the color of the compound because the color results by the excitation of these electrons when they absorb energy from the visible light. So please look at the diagram. So please look at here. So what we said that an anion. So here there should be B minus. So an anion is there. This anion is missed from its normal position and it leaves behind a hole. And in this hole, an electron will be occupied. This is an electron. And the hole occupied by the electron is called F center. So this is called an F center. Okay. And this compound will be colored. Why? Because this electron will absorb energy from the visible light for its excitation and it will make the compound is colored. So this is called the metal defect due to anion vacancy. I hope you understand. Then the examples are the excess sodium ion in NaCl which make the crystal is yellow. Then the other one is the excess potassium in KCl which make it violet. Then the excess lithium in LiCl which make it pink. Okay. The second one is due to excess cation. It means extra positive ions occupy the interstitial site and to maintain the electrical neutrality, the electron will be present in other interstitial site. Okay. The example is when ZnO is heated, it loses oxygen reversibly and turns yellow in color. So in this case also an electron is present. So this electron will also absorb energy from the visible light for its excitation. That's why the ZnO is in yellow color. Okay, the reaction is like this. ZnO reversibly gives Zn2 plus oxygen plus 2 electron. Okay, let's look at the diagram. So I already discussed that in the case of excess cation, an extra positive charge is occupied in the interstitial position. Like this. Okay, look this red box. Okay, and similarly an extra electron will be also occupied in the interstitial site. Okay, this is that. For make the crystal is electrically neutral. So this is called metal excess defect due to excess cation. Okay. So we already discussed this reaction. So consider the interstitial or the crystal lattice of a ZnO. Then the Zn2 plus ions get trapped in the interstitial site. We already discussed that the Zn2 plus ions will located in the interstitial site and the equivalent number of electron will be also occupies in the interstitial position. Okay. This effect is called metal excess effect due to excess cation. And this ZnO is an N-type semiconductor because the electrons produced is cost for the electrical conductivity. So ZnO is an N-type semiconductor. Now we are going to discuss about metal deficiency defect. What is that? Okay. This type of defect is possible in metal which shows variable oxidation state. So the metals having variable oxidation state will show the metal deficiency defect. Okay. It can be classified into two. What is that? The first one is due to cation vacancy and the other one is due to the presence of an extra interstitial anion. In first one, due to cation vacancy, a positive ion is missing from its lattice position and the extra negative charge created is balanced by the adjacent metal ion which attains one additional positive charge. The examples are FeO and Fes. Okay, please look at the diagram. The metal deficiency defect due to cation vacancy means, so here should be a positive charge, isn't it? So here should be a cation and this cation is missed from its original lattice position. So there should be a hole is there. Okay, that's why it is created an extra negative charge is created here because one positive charge is missed from the original position. That's why an extra negative charge is here created here. So this negative charge is balanced by an adjacent metal ion. How it do that? Because the adjacent metal ion will will attract one more metal ions. Okay, here the oxidation state is A plus and here it became A2 plus. So an adjacent metal ion will attract one more metal ions and form A2 plus. Here the oxidation state is 1 and here is B minus and here is A plus. Okay, and in this case this forms an additional A2 plus charge. Okay, then the FeO, Fes are the example for this type. Okay, consider the FeO lattice. Then you just assume that 2 out of 3 Fe2 plus ions may be converted into Fe3 plus and the third one may be missed from the lattice side. It means that you consider the lattice of Fe2 plus. Okay, then and it contains only 3 Fe2 plus ion. Assumes like that. Okay, in that 3 Fe2 plus ion, 2 will be converted into Fe3 plus and the third one is missed from the lattice. And this is called the cation vacancies. An electron exchange may be occur between Fe2 plus and Fe3 plus. Okay, that is why the 2 Fe2 plus is changed into Fe3 plus because an electron exchange is occurred there. Okay, in certain samples of iron pyretics have shiny appearance. Okay, because of this electron exchange, certain iron pyretic samples have a shiny appearance. This is why they are also known as fool's gold. This electron flow increases the electrical conductivity and the crystal has metallic luster. Okay. The second one is due to the presence of extra interstitial anion. It means an extra negative ion is occupy an interstitial position and the extra negative charge thus formed is balanced by an adjacent cation possessing additional positive charge. So please look at the diagram. So what we discussed is an extra negative ion is occupies in the interstitial position. So this is this one. So that's why an additional negative charge is formed in the crystal lattice. So this additional negative charge is balanced by the adjacent cation possessing an additional positive charge. Okay, this all cations charge is plus 1 and this cation charge is plus 2. So the additional negative charge formed by this cation is balanced by this cation by A2 plus charge. Okay, I hope you understand this one. Next we are going to discuss about the defect is due to impurity. Impurity defect. This defect arises when foreign atoms are present in the lattice or at the lattice site. So for example, when molten NaCl containing small amount of Sr2 plus is crystallized. Okay, then some site of Na plus ions are occupied by Sr2 plus ion. Then each Sr2 plus ion replaces 2 Na plus ion. So one Sr2 plus ion replaces 2 Na plus ion. Okay. Sr2 plus ion occupies only one site and the other site remains vacant. Okay. Here the number of vacancy is equal to the number of Sr2 plus ions. Please look at the diagram. So what we discussed here. So we are heating the molten Na. So we are crystallizing the molten NaCl and Sr2 plus ion in this case. And some of the Na plus ions are replaced by Sr2 plus ion. So here should be Na plus ion. And in this case, this Na plus ion is replaced by Sr2 plus ion. Okay. And that's why here Sr2 plus. And one Sr2 plus will remove 2 Na plus ion. Okay. So one Na plus ion is removed from here and one is removed from here. And it will make one site became vacant. Okay. So this is why the number of Sr plus ion is equal to the number of vacancy. If one Sr plus ion is here, then the vacancy will be 1. If 2 Sr plus ion is there, then the vacancy will be 2. I hope you understand this. Another example is cadmium chloride and AgCl. Okay. So this is today's class. I hope you understand this point very well. And in this class, the Schottky defect and Frenkel defect, that topic is very important.